So to get started, this is going to be an introduction to R from the standpoint of the tidyverse package, which is a really big draw to why people actually use R. So if we, the goals here, this is a brief introduction to R in RStudio, and then its emphasis on use of the tidyverse package, the functions within those, and some of the usefulness you can get out of those. The three in particular we'll be focusing on are dplyr, broom, and ggplot2 for these, but there's other functions within this package or other sub packages that have more specific uses for those. But these are the most general ones that can apply to pretty much all sets of data. If you're completely new to R and you've never used it before, then it's also good to know base R, even though in a lot of cases the tidyverse notation can be more useful. So in our in the 18STLET time repo, we have previous years where we have gone over R from base programming, so not using any packages or anything like that. That's also something you want to go through too. So to start off with, what is the tidyverse? The tidyverse is a package in R by Hadley Wickham, which is actually just a series of sub-packages that all group together and perform similar functions, most of which Hadley Wickham wrote as well. There's a picture of him up there. He's a statistician, adjunct professor, and he's the chief scientist at RStudio. And the whole concept of the tidyverse is it's a series of functions built around what he refers to as tidy data, which is a specific form of data that we'll get into here. And he actually has a paper that I linked down at the bottom on what tidy data is and why it's important. So the tidy data is another term that Wickham coined, and it is data that is in a form that is most easiest to interpret, organize, analyze, and visualize, especially if you're using data science languages like R, Python, MATLAB in some cases too. And it all sort of goes into this, the general data science pipeline of this import, tidy, transform, visualize, model, and then communicate results from there. So this data is structured in such a way that it is easiest to work through this pipeline. The main pull for the tidy data is that the columns are the variables, the rows are observations, and every single value or every single index has a value in it. And this is also not necessarily the most compact form of data. There are ways of summarizing your data into smaller chunks where you say remove replicate data that's going through. But as we'll see in tidy data, it's actually usually longer than the most compressed form it could be. And also metadata can be used to store information about subsamples within data. So some examples here of data that is not tidy data are these two down here. These are very common forms I generally see in Excel files or just other general sheets. In this one here, it's a mock reading from a measurement, in which case they've put some inputs about the test on the top. So temperature, some initial conditions, sample names, and then down here, they actually have the data. This is not a tidy format of data because these cells over here have nothing in them, and then these don't correspond to these columns. So the columns are inconsistent going across. And then another one is this format here, which is easy to look at from a human standpoint, but because these cells are merged together, then we don't have that single index has a single value to it. So this can be a bit confusing. If we look over here at an example of tidy data, this is from RStudio. It has the variables across the top as columns, and then each row is a single observation from there. So these are all the packages built into the tidyverse. Most of them have specific functions, especially the import ones. We're focusing on these four, on the ggplot, broom, and dplyr, all of which use the Tibble package. And Tibble is a tidyverse form of a data frame. The actual difference between them is usually not that important. So if we'll jump over to the script. There we go. Oh, did you have it pulled up somewhere else?
Yeah, so you can open it from here. It's an R file, right?
Yeah. Is this on HPC?
Yeah. Why we don't have.
I need 16 gigs.
I just saw that.
Is that active? Is that in?
Let's see if the R is installed.
Is this R on your local machine?
Yeah.
Then just pull the repo here.
Yeah. Because yeah, it's got installed. So open the terminal.
So you haven't pulled this at all?
Hmm?
You hadn't pulled this at all recently?
No, not since in the meantime, go to it.
No, what?
It's almost done. It's almost done.
Is it?
Yeah.
All right.
Now go to R.
All right, there we go. Let's increase the font a bit. That'll be readable. There we go. All right. So moving through this, if you haven't installed the tidyverse yet, you'll need to run this function install packages tidyverse up here if you want to follow along. If you haven't installed, then you can library it here with this function. We're going to be using the diamonds dataset as a demonstration here. So if we look at this, this is the data set we showed earlier. It's a series of just under 54,000 diamonds, and then some information about their weight, how much they cost, and then some other properties like their clarity, color, and size that we can take a look at here. So the first thing we want to introduce in this concept is the pipe, which is this operator here, percent greater than percent. And this is a very useful feature. Basically what it means is it takes the output of one function and sends it in as the input to the next one. So as an example here, if we have this just a sequence from 1 through 5, it's a vector from 1 to 5, and we can pipe this into the mean function to send that right in, and so we get the mean of that out of there. And if we want to assign that output to a variable, then we can just use our assignment operator here and pipe it in there. So now we have this median object that is the median of what we sent in there. This is very useful for stringing functions together and preventing variables in between that that you might need to temporarily hold on to some information, but you don't need at the end. So we'll see this coming up a lot as we move forward here. The first thing for this is we're going to look at manipulating data with the help of these three functions here, the filter, select, and mutate. Filter isolates rows in a data frame based on given conditions, the notation of some of which are down here. So for an example, if we look at the table, so there's several different colors within our data frame. If we only wanted to look at one of those, then we could just take our object diamonds and pipe this into the filter function where we specify color as D. And this gives us the output of the data frame, but it only has the rows where the color is D. Something else to note here is that I don't actually specify what the data is here. If I was using filter by itself, I would need data equals D as part of this, but because the pipe is before it, I don't need any of that moving forward. I can do multiple filters at once. So if I want either D or J as the colors, I can use my OR operand up here to pipe this through. And then I get both D and J colors in my final one. And then I can also filter by multiple columns. So let's say I want color is D and price is greater than 8,000. Then I can just use my AND operator in that case to get these out. And so now this final data frame will be color D, and the price will be above 8,000 for these. Select is a very simple one. It's so filter was used to select the rows you want to use. Select is used to select the columns you want to use. In this case, if I only want the price column for my D data frame, just run it through select, and now that's the single column I have. I can select multiple columns just by specifying them sequentially within the function and get those out. So that's a very straightforward one. You can also remove columns if you want by putting the negative sign before. And now I have all the columns except for color there. Mutate adds new columns to your data frame. So if I want a column that is dollars per carat or something like that, then I can mutate this function in and define it as the price divided by the carat for each input. And this is nice because it will run through all of the this will run through all of the rows, so I get a unique one for each one there. And you can run these together, just piping them one after another through if you wanted to. In this case, order is important because it will go through these functions sequentially, so you have to keep in mind what order you want these to run through. So if I only wanted the price, carat, and cut of the ideal cut diamonds, then I can filter to ideal first and then just select the 3 columns I want there. Run through that, no problem. And another example here, if I only want, I'm only looking for diamonds with a dollar per carat of at least 6,000 moving forward. First, I have to create this column, and then I can filter by it in that case. That gives us an example here. You can use pipes with non-tidyverse functions as well, but in some cases where you input the data, you will have to specify that with the dot here. So table is not a tidyverse function, but I can still use it in a pipe as long as I just use a dot to specify where the data is piping into. So in this case, it's the same as before. I'm filtering to dollars per carat greater than 6,000, selecting the cut, and then I'm seeing what distribution of cut I get through those. So if you run through this, most of them are ideal, and then it tapers down to a small number of fair diamonds. So these are useful for sorting your data, but it's just looking at data essentially. We can actually start to pull out some results if we use grouping and summarizing in this case. So summarize applies a function to obtain a singular result from a given input here. So if I wanted, say, to know what the average price is across all the diamonds, then I specify the column name will be mean, and then I want to know what the mean of the price is, and then I can just pipe my object into this, and I get out a single answer, which is the mean of my entire price column. This is a bit more coding than you would normally do for getting the mean of a column, but this has a lot more uses further down. You can specify multiple outputs too, just by stringing them together here. So if I want the median and mean of 2 different columns here, then I can run through that and I get those answers. So in this data set, we have some categorical variables like color, clarity, and cut. If I want to run analysis by groups of these, then I can use the group by function to cluster these together and then have them run by individual groups. So if I want to know what the mean of the price is for each cut of diamond, first I group these by cut, and then I pass them into the same summarize I had before. And what I'm going to get out is 5 results now, 1 for each of the given cuts of these. And you can group by multiple variables as well. So if I want to know what the median weight is for each unique combination of color and clarity in this case, then I just add another input to my group by. And you can see I have more results out because there are more combinations when adding in more variables here. So this notation is really useful for things like removing for loops from some of your code. So if we have an example here, the question is, which cut of diamond has the highest correlation between weight and price for D color diamonds of at least 1 carat? If we were going to do this with a for loop, this is the code we would use here. First, you have to assign an empty results one, then you loop through each individual cut, you subset the data down, and then you get your correlations. And then you also have to conglomerate your results at the bottom. If we run through this, it runs quickly. And so we get the cut and then the correlation for all of these. But this is, it's a little bit harder to read. And also we can see this dat variable, this core variable, and this R variable that show up are not useful. These objects, we don't need them for anything. We just need to collect them, but we don't actually need to save them anywhere. However, they do show up in our environment. So if we run this through the tidy notation, then we take our object, first we filter it, group by cut, and then we summarize. And I've added an addition here where we arrange it by descending correlation, just so we can easily see which one is the highest. And if we look through here, then we get our result as the fair cut. So it's the same result for both methods, but if you look at these two, the tidyverse way is a little bit simpler to go through, and you don't end up with a bunch of intermediate variables that take up a lot of space that you don't end up needing. This is useful and handy to use, especially if you're subsetting and trying to select specific types of data. But some of the really useful stuff you can do with dplyr is when you get into actual modeling with some of this. And we're going to be using the Broom package as part of this, which is part of the tidyverse, but it doesn't load in when you library tidyverse, so you have to library this separately. So let's say for each, if we want to know for each clarity of diamond, what is the linear model between the price and the carat? And we can do this very simply with tidyverse by, it's what we started with before. We have our diamonds data frame. We pass it into the group by for clarity. And then we have this do function, and we define our model. And then in here is the formula we want to use for this. So if we run through this, then we get this models object, which might take a little bit to load. But what this is for each clarity that we specified in the input, we actually have our linear model object located in this LM model column. So this is a very quick way of modeling multiple groups within the data at the same time. And then there's also a lot of really nice features for interpreting these models once we've got them. So here, the main one is glance. So we have this models object, and we just glance at it. And so what this does is it gives us some statistical information about each of our individual models here. So these are the different clarities we have. And then we have R squared, adjusted R squared, sigma, p-values, things like that. Then if we want a more interpretable or readable linear model format, then we can pass into tidy, and this converts it into from a model object into a data frame here. So we have this new term column that shows what our intercept and what our coefficient is for each of these, and then we get the estimate and the error for all of these going forward, and for each of the clarity. And finally, we can also use this to predict new values. So let's say, for example, we wanted to know what a 1,000 carat diamond would cost for each of these given clarities that we've built these linear models of. Then all we need to do is create this data frame of our prediction value, and then we pass this into the augment function. with our model and the data we're predicting with. And then out of that, we can get this fitted value of this prediction for all of these models. So this is a really useful aspect of tidyverse, and this is something I use a lot in my own research because I end up doing modeling by individual days, weeks, or months in some cases. So I can have an entire data set and I can still build these models, but I don't actually have to run through with for loops or cut down anything. I can just build this side object that has all my models contained in it and work with these very nicely. So this is some of the functionality that I find most useful for the tidyverse. If we move on to ggplot2, which is the visualizing aspect of this, I agree that in. This is part of the tidyverse it's built solely around plotting data and observing data. And the notation for this is it builds plots in layers and you add them on sequentially. So let me move this over a little bit here. If I run this one, the main function is ggplot. So we'll see that a lot. And then I have to define my data, which is the diamond data frame again. And then this aesthetic term, which we'll talk about more in a bit, but I want to plot the price of the diamonds versus the weight of the diamonds. So if I run this, then I'm actually not going to get anything. It's going to be a blank plot because I haven't specified any visual layers on this. I've just defined a graph where x is the carat, price is, or sorry, x is carat, y is price, but there isn't any data in there yet. So to do this, all I need to do is plus, and then if I want a scatter plot, for example, I just add this geom_point layer here. So now if we run this, what we're going to end up getting is the same structure of plot, but now there'll be this layer of scatter points on top that we can observe. So we see that right here. It's the same blank plot we saw before, but this layer has been put on that shows the data in the format we specified. Something else you can do, you don't have to specify the data in the ggplot function. You can just call the empty ggplot function and then specify the data and the aesthetics within the layer that you've assigned this to. The only thing that you have to do with this is you have to type out data equals whatever your data frame is. If you don't have this notation in there, this will not work. But this can be very useful if you have very different aspects between your layers. So this allows you to tailor individual layers a bit more specifically. And then you can plot in groups as well. So let's just get this started. In this case, I have my x is carat, y is price. But if I want to look at differences between cut as well, then I can just specify that the color of this data is going to be determined by cut here. And when I run that, then I have my cut variables have been distributed out into individual colors and assigned to the plot. So now I can very easily see which cuts correspond to which data point for these. So if we talk about this AES function right here, what actually does this do? This is the aesthetic function, and it defines the features that vary with the data. So if anything that is influenced by the data needs to go inside the aesthetic function. If it is a property of the layer, then it goes outside. So an example of this here is I can plot this one here. So I've got doing a scatter plot again, and I've specified color is cut and size is clarity. It doesn't like that I use size for a discrete variable, but that's okay. And so you can see here when this normalizes again, but now my data is also, the data points are sized based on what the clarity of them is. But that's not terribly visually appealing. If I want to make a change that does not affect the data, so here I have color and size, but they're outside the aesthetic, then they're no longer a function of the data. They just happen to be a property of the layer. So in this case, I've defined color as red and size as 3. That means that all the data in this layer is going to have a red color and a size of 3, and that is just universal across all the data points. So the data itself does not actually change any of this. And this can be useful. Coloring layers is pretty useful. size too if you want to make your data points a bit larger, but that's how you do that. Do you have a question?
Yeah, how do you just, so the previous example in which the color was in the aesthetic as color versus cut.
Right.
Like, R picked a color palette. How do you tell it make there this color? Can you define those things?
Yeah, you can absolutely define stuff like that. And this digs into a lot of the detail that I really don't get into in this. But yeah, this is really just scratching the surface of ggplot. It's very easy to define what your range of colors is for things like this. That goes into the theme call you can use later on. But the main one you can do is you can define a start and an endpoint color. So you can say, instead of the default colors, go from red to green in this case, and it will scale that continuously within there. So that would be more specific to what you actually wanted with that, if it was continuous or categorical. But that's something you can very easily control. If you want to make multi-layer plots, so as an example here, let's make a box plot. So I've made a box plot of price versus color here. If I want to add another layer to this, then all I need to do is specify that in the call here. So I have the same code as above. It's the same box plot, but then I'm adding this geoPoint layer, and I'm adding this jitter here. So I just move the data points a little bit around. This makes it a bit easier to see where they actually are, so they don't overlap as much here. But if we look at that, it's a bit hard to see because it's zoomed in, but I have my box plot layer, and then I've added this scatter plot layer on top of this. And this is where ordering gets important. So because I've specified my point layer after my box plot layer, it's going to be on top. If I wanted to put the box plots above the point layer, then I would want to specify the point layer first and then the box plots after in that case, because this isn't a very useful plot. This layer doesn't really show me anything. ggplot can also integrate perfectly normally with pipes here. So if we see a lot of this, what we saw before, we can take this data, manipulate it, and then send it straight into our ggplot call here. And we do not have to specify the data as before because we're piping it in. So in this case, we're looking at dollars per carat of only the color D, and then we're making this box plot by clarity. This shows a bit more variation than before, but if you want to organize your data and then pipe it in, that works totally normally. Oh, here's an example of the box plots being switched. So if I do the same thing as before, but then I just specify the geoPoint before the geoBox plot, then they appear in front. And I've made my box plots red just to make them more visible here. You can see that I did that just by specifying color equals red outside of the aesthetic call. To control your appearance, there's a couple ways to do this. There's actually a very large number of ways to do this, but what I found the simplest ones to do are to use the labs call here to input labels to this, and then you can use theme to control things like legend position, names, font size, and things like that. So as a quick example, I'm adding some labels here for the X, Y, and title, and then I'm increasing my font size to make that a little bit more visible. So we can see here now this is a lot more readable than it was before. I have proper AXI names with units and things like that, and a title on that. You can also change the overall style of it. So this gray background is the default. I don't really like how it looks that much. My favorite theme is this black-white theme here, but there's a whole number of these themes you can use based on what you want your graph to look like. So this is the black-white theme. It has an outline box and then some subgrids, white middle. This is what I like to plot with generally, but you can pick whatever you like. It's a lot of variety here. So another important thing with this is faceting. If we remember in this cut variable, there's 5 different cuts. If I want to plot a plot for each of the cuts, then instead of making 5 separate plots, I can just use this facet wrap here. So if I want to plot price per weight for each individual cut, then I can just specify this here. It's my normal plot, but then I pass it into this facet wrap, and I want it to distribute by cut, so I use this tilde cut call. And then some extra information here, I can define how many rows and columns I want in here. So you can see the final data frame is actually 5 separate columns, 1 for each of the cuts, and then the price per carat for all of these. So this is very useful for saving yourself repetitive plot making to move forward and keeping everything nice and organized. You can also add linear models to plot. Do you have a question?
So what's the data type?
Oh, for cut? So it's, as it is now, it's a Tibble. And Tibble is much better about factors versus characters. If it was a normal data frame, it would have to be a factor, or else this would not work. That's a little bit of detail. Make sure that these variables are factors if you're sorting them by groups. Factors and characters are very similar, but characters have no grouping value to them, but factors do. So if you have a column of factors, then it knows that all the cuts of the same name are in the same group together, and that's how it can split these up properly. If this was a character and I did this, I would get a single graph for each individual row, because it doesn't know that two characters that might be the same are actually the same group. So that's something to look out for. But if you stick with Tibbles, you really don't have to worry about that at all. That's only a problem for data frames. You can also add linear models to these using this geom smooth. You have to define the method. In this case, I just want to add a linear model, and this is still going into the facets. So it's the previous graph we saw, just with these linear models added onto these. So you can see those here. There's a number of different types of plots you can put on here, and you can add separate ones as well. This function tends to get a little bit limited, in all honesty. I would recommend, if you're trying to add more complex models to graphs, to make a separate data frame from them and then plot them together as separate data. You might want to avoid using geom smooth, but it's something you can look into more if you're trying to do something simple like a linear model. And then if we get into some more specific plots down here, these are just examples of some other things you can run through with this. So these are bar plots. These can be very useful for showing some categorical data here. So this is the cut, and then we can see the distribution of clarity in here. And I did that with, instead of color, I used fill. So for bar plots, color is the outline, not the middle of it. So I use fill to actually fill the color in. And then in geom bar, I've specified black's the outline to give these bars here. If I remove this, then they don't have outlines to them. It's just the colors running up against each other. That's not as easy to see. We can do density plots as well, which are a good way of looking at dense 2D data like this is. These don't show the data points, they show the areas of density of the data points here. So we can see as before, most of the data is clustered down here, then it spreads up, and we also have this group out to the end. I've grouped this by cut as well, just to show it's possible. This probably isn't necessary for something like this though. And then there's another way of showing dense data is a hex plot, which is plots by location and then density within those. Explain required for staff. I think there's this must be an older version of tidyverse on here. But this should work on the most up-to-date versions there. And then line plots, we actually haven't shown a line before, but that's because we really didn't have the data for it. This was mostly scatterplot data. But if I want to, I can throw a line up there. I just use this geom line call, similar to that. So now I have the points and the lines connecting them. Something else I wanted to add to close up with, if you're plotting multiple curves, then you can specify a color within each one. So we're going to use a different data set here. This is the MT cars data set, which has more continuous variables. But if I want to plot two different columns on the same graph here, then what I showed before, I can specify the aesthetics within each individual layer. And then if I add this color equals displacement, then I'm assigning that data this displacement factor to it. And I can do that for these two layers and these two layers. And this builds this legend here at the end, which is very useful if you're plotting different kinds of data on the same graph, and especially if you're trying to do different kinds of plots. So if you're trying to put points on a line plot of different columns, then this is, in my opinion, the best way to do this, because you can easily specify what each layer is, and it'll all appear on the same graph, and you'll have a continuous legend for that. So that's what I have for my demonstration. Are there any other questions on tidyverse in general or plotting? All right, thanks. Which one is the